than K2. Means that this reaction with the arrow, you see the arrow big and thick, is faster than this arrow. That is what I said by words without picturing that out early on. So it means that this guy here will never be able to reach equilibrium, so K minus 2 and the backward reaction will not happen, but this one will. All right? So the second assumption is the steady state assumption. And it's very simple. In the reaction, we just put a ton of substrate. A large amount of substrate, much more than the enzyme that is there. When this happens, and this is the graph that represents that, if we have a lot of substrate at the beginning, quickly the enzyme substrate will build up until the concentration of ES will be pretty high. The majority of enzyme will be in that form of binding the substrate. We don't know yet how much, but it will be high, and will be constant for a long time. Because even though S will be transformed in P, there will be still a lot of S getting there and be transformed in P. So the derivative of ES divided derivative of time, since ES is a constant value for that time space, that is equal to 0. That is very important, okay? Because it simplifies whatever we are going to do next. So the other thing that is written here is this one is just a way to rearrange this simple equation that is pure common sense. Total enzyme is equal to the free enzyme, which is this guy here, plus ES. Is obvious, right? So, do you guys want me describing more this graph here, or you are good with that? You know, there is 4 colors, so I hope it's not too complicated. There is the substrate concentration up here. The enzyme concentration, total enzyme is here. But this total enzyme becomes free enzyme there, and the ES is raising up there. And finally, there is product line that is going this way. While S is declining, the product is increasing. And these, of course, are this time versus concentration. No difficult. All right, so step 3. Since derivative of ES divided derivative of time is equal to 0, the question that we built just a moment ago can be rewritten, because this guy goes away, but and there will be nothing. There will be a 0. 0 is something. So we can rearrange this one, writing that in this way. And then we can isolate on one side the concentration values, on the other side the rate constant values, and we define that as Ks. Pardon me, Ks. So concentration on one side, rate constant on the other side. This is the Michaelis and Menten constant. The unit of this constant is molarity. So when you see in a graph the rate of reaction versus the concentration of the substrate, sometimes instead you have the S for substrate, there is K con M, but it's the same thing, okay? It's the concentration, could be K con M, could be 2 times K con M, could be 4 times K con M. Imagine K con M to be 10 powers to minus 3 molar. So that is 10 powers to minus 3 molar concentration of S. I forgot that mention here, but it's cool. So we are done, basically, because by rearranging all these parts, we get that which means we had a V0 in part 1 equal to K2 ES. Now we have a definition of ES, which was all this part here. Please. I mean, yeah, it's not written here, but you can isolate ES from all this. And once you have that, you can substitute this guy with that and write this part. Let's focus to this K2 total enzyme. K2 is the slowest and rate limited. So it means that the reaction, overall reaction, will follow that reaction rate. So in this case, in this particular case, K2 is basically equivalent to the catalytic constant of the reaction. In other types of reaction, when there is no this assumption, K cat could be the combination of different rate constant. It could be much more complicated. Here is very simple. It's equal to K2 at 99.99%, so no bigger complication with that. But K2 or K cat times total enzyme is nothing else than say Vmax. Okay? So we can change this way to written here into Vmax, and we have V0 equal to Vmax times concentration of the substrate divided K con M plus concentration of the substrate. That is the Macquarrie-Menton equation for the simplest reaction that we can imagine. So what we can do now? We go back to our memory to what we did with myoglobin, because the curve is very similar to myoglobin, even though myoglobin had the Y2 here, YO2, and here there was the concentration of oxygen in the form of gas. In this case, we have a concentration of the substrate and rate of reaction. As usual, we look at the 50%. In this case, will be 50% Vmax. Why we do that? Because since it's a rectangular hyperbola, it's hard to figure out the total value. You have to go really to high concentration. You tend to there, but you never reach it. But it's easier to see alpha beta, and that will give you the idea how much is that alpha value. So when we identified alpha Vmax here, and we intersected the curve, on the x-axis we will find K con M. Or otherwise, we can say, like something that you learned maybe first year in chemistry or biology, that when the concentration of the substrate of an enzymatic reaction is equal to its K con M, the rate of reaction is equal to alpha Vmax. Got? When the concentration of the substrate is equal to the K con M of that reaction, the velocity of the reaction is equal to alpha Vmax. Alright? So what happens if K con M changes for some reasons? If K con M becomes smaller, there is a higher affinity of the enzyme for the substrate. Remember, Vmax don't change, so also alpha Vmax will not change. But if you need less substrate to reach that level, it means that the affinity of the enzyme for the substrate is increasing. So if K con M is smaller, affinity goes up. If K con M is bigger, affinity goes down. Because again, you need a ton more of a substrate to be able to have the enzyme going to alpha Vmax. What is that? Oh, actually, whatever I said should be, it's basically a bigger picture of what I said. K con M contains also Ks, things like that. That is another lecture. Oh, yes. What we are looking here You remember when we looked at the graphs of hemoglobin and myoglobin, and I told you, there was the goalie guy that experiment at the game, and the goalie was trying to catch 4 soccer balls with all his limbs. So that is like was the case of hemoglobin. And as I imagine you being all the class with that, because what we analyze is a flask, a container with a bunch of enzymes. So this curve is nothing else than representing X amount of enzyme with Y amount of substrate producing some Z amount of product. Okay? It doesn't tell you the rate of a single enzyme, what a single enzyme is doing. That one is K-cut. Okay? While this one, with the mechanism and the equation, is just the analysis of a population. And I put here, usually it's when I have your grades today, and I hope you are not mad because I improved the curve. Okay, there was few students that did very well. No one mistake. By the way, I gave there was an error on the exam. There was 2 exams that had a repetition of one question, so I gave it to everybody else 3 points. Okay, I made more equal that the perfect judge in this world will do. Okay, so it is going to be good. And plus I did the correct. So I'm saying you should not be mad, but usually when students are mad, I play the game that you are all enzymes in this class, and there is a bunch of pencils that are the substrates, and you break the pencils because you don't want to break my neck, but you break the pencils, okay? So that is the rate of reaction. And the rate is all the class, how many pencils are broken per second. But, if we take one single student, how much he or she will break might be slightly different. That is the rate of one of only you, and that is the K-cut. Here we are with the K-cut. K-cut can be calculated in this way, Vmax divided total enzyme, and for our specific example is equal to K2. Other times is a combination of different rate constant on that reaction. So we have here a table with different K-cuts and K-con-Ms. K-con-M very small, usually, K-cut very high. There is also a ratio between K-cut and K-con-M that explains the efficiency of an enzyme, enzymatic reaction. When K-con-M is very small, means the enzyme has very high affinity for the substrate. And K-cut is very high, means the enzyme is very fast. That is a big number. In fact, all these are very big numbers. When they get really big, then we will see an example during glycolysis. Means that that enzyme is so fast that whenever it's even seeing a substrate, boom, that substrate is transformed. So the rate limiting is only the diffusion of the substrate itself. And enzymes can work near diffusion control in that example. The enzyme is TIM in glycolysis. And that happens when this ratio is like 10 power to 8, 10 power to 9. All right, so finish the review. Good timing for most. So let's take attendance, and now we just have an introduction of inhibition.